In today's lecture, we'll introduce the concept of complex numbers, we'll show some properties, and see why we care about them. So to begin with, when we have just real numbers, the numbers we've been using so far, we can solve any linear equation of the form ax plus b equals 0 here. No matter what a and b you pick, we'll always have some answer. As a matter of fact, it's not too hard to find what that answer will be. It'll be negative b divided by a. However, this isn't true for quadratic equations. We can find a very easy example, such as x squared plus 1 equals 0, and try to solve, and we'll come across a problem. So we take it, we subtract 1, and we have x squared equals negative 1. Take the square root of both sides, and we come up with x is equal to plus or minus the square root of negative 1, which is not a real number. So mathematicians looked at this and they said, now what? How can we fix this problem? And what they did was simply add the square root of negative 1 as a new number, and they called it I. So anytime you see an I in a math equation, that's actually the square root of negative 1, and when we threw that one number in, everything started working beautifully, and we were actually able to solve every single quadratic equation by just adding in I. Now we called this new set of numbers imaginary numbers because when we graph them, they're perpendicular to real numbers. So what's completely different from being real? Well, being imaginary. And we gave them the special name I because they introduced a new axis of numbers to work with. So now, when we're looking at a number line, when we start working with real numbers and imaginary numbers, it actually is a plane instead of just being a one-dimensional figure. When we work with these, what we used to think of as the x-axis now becomes the real axis, the numbers we're used to working with. And what we called the y-axis before, now we call the imaginary axis. These are where we put our imaginary numbers. And graphing them is quite easy, and it's very similar to graphing numbers on our equations. All we have to do is find, okay, how far do I want to go out on the real axis? Maybe to 3 here. How far do I want to go on the imaginary axis? How about we go down to negative 2i? Then we plot the points. And now we just add these two numbers together, 3 minus 2i, and this entire combination becomes our new number to work with. And maybe we'll do just a couple more. If we want to keep real numbers, then we just need to grab numbers on the real axis, such as right here, just the number negative 2. And if we want to grab just imaginary numbers, we just go on the imaginary axis, such as this point right here, which is just 4i. And then if we want to combine real and imaginary numbers, then we treat it exactly like we do x and y coordinates. So how about this point, 2 plus 3i. Maybe we'll grab another one over here. How about negative 4 plus 2i. And maybe one more in this third quadrant. How about right here, negative 3 minus 3i. So now our numbers are sort of two-dimensional, and in general we need to combine real numbers and imaginary numbers. And so we came up with a new name. We called these complex numbers, because what could be more complex than combining real and imaginary things? Now we denote complex numbers with this fancy C here. And sometimes we save time by just writing the C instead of saying the complex number. And generally, when we write these out, we write them in what we call standard form, which is a plus bi. Now the a is the real part, and the b is the imaginary part. However, for these, a and b are both real numbers, and all of the imaginary information is contained in the I. So if we want to start talking about imaginary and complex numbers, we need to make sure we have the nomenclature down here. So for this one, 2 is our real part, and 3 is our imaginary part. Similarly, for the next one, -1 is the real part, and whatever number is attached to the I, in this case 5, is our imaginary part. And we can have simply real and simply imaginary numbers still being complex. I can write 4i as 0 plus 4i. So 0 is my real part, and 4 is my imaginary part. And I can do the very same thing to 7 down here. Instead, I write it as 7 plus 0i. So here, 7 is my real part, and 0 is my imaginary part. Okay. So a lot of times when we have complex numbers, they're given to us not in standard form, and we want to be able to change them into that. And the way to do this is pretty simple. All we have to do is find the hidden I and pull it out. So let's do one example here. And let's write 5 plus the square root of -9 in standard form. So it already looks like we have our real part of 5. And now we need to fix the square root of -9 to make it look like some number times I. All we have to do is change what's written underneath the radical to be 5 plus +9 times -1. Now if we have multiplication or division in our radical, we can simply separate these terms out and write it correctly. 5 plus the square root of 9 times the square root of -1. Remember, this only works for multiplication and division, not addition and subtraction. And with this one technique, we've found our hidden I, and now everything looks much nicer. We can take the square root of 9. This is just 3. And then the square root of -1 is exactly what we call I. So 5 is our real part. And the square root of 9, or 3, was our imaginary part. Okay, so let's look at some simple facts about I here. I is a very nice number, and it actually loops around. It can't get too complicated. So if we start with the original definition of I, we say I is equal to the square root of -1, and then we'll start squaring it. So here, I squared, this should be the square root of -1 squared. Squares and square roots cancel out, so all we're left with is -1. So I squared actually becomes a real number, and that number is -1. Now let's look at I cubed. We can write I cubed as I times I squared. We already said I squared is -1, so this is actually I times -1, or -I. So when we cube I, it actually goes back to the first power and picks up a negative in front of it. The only remaining case is I to the power 4, which we can actually write as I squared times I squared, which is -1 times -1, which is 1, and now we've gone back to our original number, 1. So if we have just I, that's the square root of -1, I squared flips over to be -1, I cubed flips over to become -I, and I to the 4th moves around to become just 1 again. So I is actually very closely related to our original number 1. At this point, things start looping. We can write I to the 5th as I to the 4th times I. I to the 4th is 1, so 4 of our i's go away, and we're just left with I again. So this pattern loops forever. We can always simplify our imaginary parts to be either I squared, I cubed, or I to the fourth. Once we know these simple facts, we can start doing algebra with complex numbers. So we'll look at addition, subtraction, multiplication, and division, and we'll see how to handle these things. So first, let's note that if we have two complex numbers, a plus bi, we say that's equal to c plus di. This can only happen when the real parts are equal and the imaginary parts are equal. So only if a equals b and c equals d. The second fact is that when we do our algebra, we always want our answers in standard form. So we'll finagle them just a little bit, so they always look like some real plus imaginary part times I. Alright, with that in mind, let's get started. Addition and subtraction are actually pretty simple. Everything works quite nicely, and we can drop the parentheses here and start combining like terms. So we'll start by adding the real parts, and we'll get a plus c. And then our algebra says we're allowed to combine the imaginary parts. So this is plus b plus d, and they both have an I in there, so I can just factor it out. So my real part becomes a plus c, my imaginary part becomes b plus d, and now it's in standard form. Subtraction is just as simple. This becomes a minus c plus b minus d times I. And this is because we need to remember that if we have a subtraction sign, it always carries into our parentheses and hits both terms. So this is really a plus bi minus c minus di. Alright, so let's give it a shot here. Our example is 2 plus 3i plus 6 minus 2i. We have a plus sign in the middle here, so we need to use the top formula, and it says we add the real parts and we add the imaginary parts. So this is 3 plus negative 2 times I, and our final answer is 8 plus 1 times I. So addition's pretty simple. We just need to remember real goes with real, imaginary goes with imaginary, and we need to make sure that our plus signs and our minus signs line up correctly. Multiplying is a bit of a different beast. So again, the general algebra rules apply, and we're going to FOIL out our two imaginary numbers to come up with something we can use. So let's start foiling. If we remember the rules, for foiling, first it is the first two, so a times c, plus outer, a times d times I, plus inner, b times c times I, plus the last two, which is b times d times I times I. Now let's rearrange this just a little bit. This is AC plus ADI plus BCI plus BD times I squared, and we're not in standard form yet. We have this I squared term which we need to simplify, because remember in standard form we only have i's, we don't have any higher powers. So we know I squared is equal to negative 1, so this actually becomes AC plus ADI plus BCI minus BD, since I squared is negative 1. And now we can group like terms. So this is equal to A times C minus B times D for our real part, plus A times D plus B times C times I for our imaginary part. And now again, this is in standard form. Some nice real number with no I plus some nice real number times I, and things are separated out quite nicely. So remember, when we multiply, we just need to FOIL, and I squared is equal to -1. So let's do an example here. Okay. So again, we'll just FOIL and follow the rules. 2 times 4 is 6, plus the outer 2. So this is plus 2 times 3i. Now the inner 2, plus -4i times 3, plus the last 2, which is -4i times 3i. So we have 6 plus 6i minus 12i plus 12. Again, it becomes plus 12 because if we actually work this out here, we get that this is -12i squared, which is -12 times -1, which is 12. Okay, now that everything's in place, we can combine our like terms here. 6 plus 12 is 18. 6i minus 12i is minus 6i. And we have our answer. 2 minus 4i times 3 plus 3i is equal to 18 minus 6i. And this is all there is to multiplication. Now before we define division, we need to come up with one more term. And this is the complex conjugate of a complex number. So the complex conjugate of a plus bi is a minus bi. The reason why we need to change the imaginary part comes when we multiply these out here. So a plus bi times a minus bi becomes a squared plus abi minus abi minus b squared times I squared. Notice that our middle two terms are the same, and they're going to cancel out. And minus b squared times I squared will become plus b squared, since again I squared is equal to -1. So when we multiply two complex numbers together, and their complex conjugates, we always end up with a nice real number. So we can now use this trick to simplify division into dividing by real numbers, which is our end goal. First, to make sure we understand, let's multiply 5 plus 2i times 5 minus 2i. Now if I follow my formula, this should be the real part squared, which is 25, plus the imaginary part squared, which is 4. So this should just be the real number 29. And if we FOIL it out, we'll get 5 times 5, which is 25, plus 10i, minus 10i, minus 4i squared. Again, the middle two terms cancel out. I squared is equal to -1. So this is 25 plus 4, which is 29. And the shortcut works. All right. So how will we use this technique for division? Well, let's give it a shot. So in general, if we're dividing two complex numbers, it just looks like a plus bi divided by c plus di. And remember, our goal is to write this in standard form. As it stands, it doesn't seem like there's too much we can do. So the trick involves multiplying by the same thing on top and bottom to make this simpler. And what will we multiply by? Well, if we want to change this into a real number, well, we have a formula for that. If we multiply by the complex conjugate, no matter what complex number we have, it always simply becomes real. So we'll do just that. We'll take 2 plus 3i divided by 4 minus 2i, and we'll multiply by 4 plus 2i divided by 4 plus 2i. If we do the same thing on top and bottom, it doesn't change anything, since this is really multiplying by 1. Now we'll group up and simplify. This becomes 2 plus 3i times 4 plus 2i divided by 4 minus 2i times its complex conjugate, 4 plus 2i. Now we just need to multiply and work things through. Okay, so let's FOIL out the top. This becomes 8 plus 12i plus 4i minus 6. And again, this 6 here is by multiplying 3i by 2i. And on bottom, since these are complex conjugates, this should just be the real part squared, 4 squared, plus the imaginary part squared, 2 squared. And now we can simplify. 8 minus 6 is 2. 4i plus 12i is 16i. And on bottom we have 16 plus 4. So this is 2 plus 16i over 20. And since we have only one term on bottom, we can actually write this as 2 divided by 20 plus 16 divided by 20 times I. And now we're in standard form again. A real number plus a real number times I. And maybe we want to simplify this down and say that this is actually 1 over 10 plus 4 over 5 times I. And this is okay too. But if you just end right here, then you don't have to worry too much about making any errors. However, on the homework they might ask you to simplify it completely, and you'll have to fix these fractions just a little bit. Alright, so now we know how to add, subtract, multiply, divide. And our question is now, why should we care? Well, we've seen that if we're finding zeros of our quadratics, ax squared plus bx plus c, sometimes we end up with weird equations when we're using our quadratic formula. So remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. And sometimes this square root part can be negative. Up until now, we've never had a way to deal with this. But now that we know some stuff about complex numbers, we can actually simplify these equations and continue factoring down our polynomials into linear terms. So let's give this a shot with 3x squared minus 2x plus 5 equals 0 and see what we get. So for this example, a is equal to 3, b is equal to negative 2, and c is equal to 5. And now our quadratic formula tells us the zeros are 2 plus or minus the square root of 4 minus 4 times 15 divided by 6. So this becomes 2 plus or minus the square root of 4 minus, let's see, 4 times 15 is 60 over 6. And we'll get here that this is equal to 2 plus or minus the square root of negative 56 divided by 6. Okay. So before, we would be stuck here. But now, we can continue going with this example and find our zeros by using just a little bit of knowledge about complex numbers here. So the next step is, we write this as 2 plus or minus the square root of 56 times the square root of negative 1 over 6. The square root of 56 we can simply write as 2 plus or minus square root of 4 times 14. And now the square root of negative 1 becomes I all over 6. Here, the square root of 4 is 2. So this becomes 2 plus or minus 2 times the square root of 14I over 6. And then we can simplify, get rid of the 2's on top, and the bottom becomes a 3. So this is 1/3 plus or minus square root of 14 over 3 times I, and here are our zeros. So before, when we couldn't solve our quadratics, with a little knowledge about complex numbers, we can actually arrive at zeros and continue factoring things until we've got nothing but linear factors left. Now why do we care? Every polynomial of degree n has exactly n zeros in the complex numbers. What this means is that if we have any polynomial, if instead of working in the real numbers, we work in the complex numbers, then we can find every single root or every single zero of every single polynomial. And now we don't have to worry anymore about running into these square root problems. We can start factoring and get some nice results. So in the next section, we'll start looking into these zeros and how we can find them, and we'll start fixing some typos here.